Hello gems, welcome back to another video. In this video we will be discussing all the concepts from the chapter of electrostatic potential and capacitance, which is chapter 2 from your 12th standard. In the previous class we discussed all the concepts from the chapter of electric field and charges, which is the chapter 1. If you wish to go and watch that video, it's just 1 hour. We discuss all the concepts in just 1 hour. Okay, so if you want to watch that video, I will make it available in the description box of this video. Okay, this video is perfect for all levels if you are preparing for boards, JEE, NEET or BITSAT. Okay, so we have it all covered. Let's begin with the video. I did this chapter into 14 major sections and we'll be dealing with them one by one, and just like that we'll wrap up this chapter. Okay, so I request you for the next 60 to 70 minutes of your life and just put aside everything, all the distractions, just focus and let's get this done. Okay, so the first section is electric potential. So let us understand what this electric potential is via its definition. So the definition says that it is the amount of work done. So this is specifically the definition of voltage at a particular point. Okay, voltage at a particular point P. So voltage at a point is defined as the amount of work done in bringing a unit positive charge, basically having a magnitude 1 plus 1 unit positive charge from infinity to that point. Okay, so the potential at point P is the work done in bringing the charge from infinity to that point P divided by the charge. Here the charge is unit, so here the value is 1. So basically the work done will be equal to the potential. That is how the potential is defined. Okay, here we define it in terms of external force, work done by the external force. You can also say it in terms of electrostatic force. We'll see the relation. So basically they are acting in opposite sense. Okay, so now this is for the potential at a point P, right? Potential at point P is the work done in bringing the charge from infinity to that point P divided by the charge. Okay, now you can note that the SI unit of this, you can deduce it from here only. Work is measured in joules and charge is in coulombs. So joules per coulomb, or as you might know from your lower classes, that voltage is measured in volts, right? Potential is measured in terms of volts. Now it is a scalar quantity, of course, because work is scalar and charge is also scalar, right? So combination of scalar, electric potential is a scalar. Okay, this will imply a lot of things later. So remember that this is a scalar quantity. Electric field is a vector, electric potential is a scalar. Okay, now let's try to define this potential in a general way. Okay, now we'll define potential difference. This was potential at a particular point, right? Particular point P. It is bringing the point from infinity, from charge from infinity to that point, right? Now let us try and define potential difference. What is the potential difference between any two points in the space? Okay, so here we will get the potential difference, right? So VB minus VA will be similarly work done in carrying the charge from A to B. Okay, VB minus VA will be work done in carrying the charge from A to B, because external force is acting against the cause. Okay, you will understand this better when we come to a numerical. I'll show you all the things visually. Okay, so just for now, remember that external force will always act in a opposite manner, which implies that VB minus VA will be work done from A to B. Okay, VB minus VA work done from A to B. Remember that. Okay, divided by charge, of course. Okay, so similarly this will help us for numericals. I told you you can express this in terms of external force or electrostatic force. So just now we said you can take this Q naught over here. So suppose in a numerical you are supposed to find the work done by the external force and the electrostatic force. The work done by the external force from A to B in carrying the charge from A to B will be Q naught times the potential difference between them, and it will be VB minus VA, because external force is acting against. Okay, remember that it is acting against the electrostatic force. Okay, so VAB, carrying the charge from A to B, external force will be Q naught times VB minus VA. Okay, sorry, WAB. Okay, and here WAB will be Q naught for electrostatic force. Okay, it will be basically negative of that, so VA minus VB. Okay, so these two forces are acting in opposite senses. Okay, we'll understand this better by visualizing in a numerical. Don't worry about it, just focus on the definition, just the general thing, just remember the results and we'll visualize it in the next section. Come to this question, this will better help us at visualizing the concept over here. So here we are supposed to find the work done in moving the electron from B to A. You can mindlessly use the formula, you will get to the correct answer. The potential at A is given as 20, B is given as minus 40. Okay, so let's try and visualize this. Okay, so here we have 2 points in space, A and B, their potentials are given. So if you see, this is a higher potential because this is negative, right? So this is positive, this is obviously the potential at A is greater than potential at B. So the field lines will be from A to B, okay? Higher potential to lower potential. We will prove this in the following section, that the potential, the direction of the electric field is in the direction of the decreasing potential. Okay, for now you can remember that the field lines will be in the direction from higher field to lower field. Okay, so here the field, this is the direction of the field, not exactly, but we'll assume it will be from A to B, okay, somehow. Okay, so this is the direction of the field. We have to move an electron from B to A. Now you can see that since we learned this in the previous class, F is equal to QE, right, QE. So here it will be minus QE, minus EE, we can say. The charge on the electron is minus E. So we get minus EE. So basically the force and electric field are in the opposite direction. The force acting on the electron is from B to A. Okay, so the force, this force is itself helping this motion. Okay, we want to move the electron from B to A, and the electrostatic force is also in that same direction. Okay, so this work done will be positive. I'm just guessing. Okay, you can just plug in the values and you'll get to my answer. Okay, and similarly, since these two works are opposite in signs, okay, so this will be negative. Okay, basically you'll have to do external work. Okay, external, you have to, this is electrostatic force, right, Fe. So you'll have to apply some external force for this motion to stop accelerating. Basically the work that I described in moving from A to B, okay, that has to be brought up without any change in the kinetic energy. Okay, that was the underlying concept. So you have to make sure that the speed of this electron does not change. Okay, so you'll apply some external force, maybe same in magnitude, so that these two forces cancel out, and basically the electron travels with some uniform velocity. Okay, so these two forces should be about equal. Okay, so that is the underlying concept. Okay, so these two forces are opposite, hence their work are negatives of each other. Okay, so now you know why this is happening. Okay, so you can see that external force is against the motion. Okay, and hence, okay, so we'll find now, if I have more points I'll elaborate. So we have to find work done from B to A by the external force. Now for the external force, I told you it is against, so it will be VA minus VB, right? So if it's from B to A, it will be A to B. Okay, VA minus VB, the potential difference will be from A to B. So the charge is minus 1.6 into 10 to the power minus 19 charge on the electron. Don't forget the minus sign, okay, or else it will give you the error in the answer. Basically it will give this answer as positive, which it should give as negative. Okay, so VA is, if you see, 20 and VB is minus 40. Don't forget the signs. Okay, it is very important because potential is a scalar. You should not forget about the signs. Okay, so here we get how much is this? 40 plus 20, that is 60. So 16 6 is 96, or I can say minus 9.6 into 10 to the power minus 18, and everything is in standard units, so this will be joules, right? So similarly you can find the force. This is due to the external force, right? Similarly you can find work done from B to A due to the electric force, which will be negative of this basically, so you get a positive answer. Okay, why are we getting a positive answer? You have it visualized here, right? Because the electrostatic force is itself helping the motion from B to A. Okay, that's why we have a positive work. Okay, force and displacement are in the same direction, positive work. Force and displacement are in the opposite direction, negative work. Okay, it was that simple. So that is the concept behind it. Okay, so you can try the numerical yourself by replacing this electron with a proton. Tell me what changes. Okay, so that's about this question. Over to the next one. Section 2, here we will be discussing about potentials due to different charge systems like point charge, system of charges, and even a dipole. Okay, here we will be looking only at the final results. Okay, we will not be deriving them. If you are curious about the derivations, you can join me in the next video wherein we'll be discussing all the derivations from this chapter in one shot. Okay, so for now we are just looking at the results and the key concepts, okay, so that we get the gist of this chapter. Okay, so here we have point charge. So for a point charge q, the potential at a distance r, okay, potential at a distance r at a point p. So at point p the potential is given as kq by r. Okay, it's a result, we'll be deriving it in the next lecture, okay, in the next video. So here k is basically 1 upon 4 pi epsilon naught, if you remember it from chapter 1. Okay, so here it is important that you remember potential is a scalar and you have to substitute q with signs. Okay, substitute the value of q with signs. Okay, whatever the sign q has, if it's a negative, substitute it with negative. If it's positive, substitute with positive. Okay, the sign matters over here. Let's come to system of charges. So system of charges, if you have different point charges q1, q2, q3 in space, okay, and you want to find the resultant field at the point p due to all these charges, so basically you'll have to sum the individual potentials. Okay, no superposition theorem over here, you basically sum it with the signs. Okay, whatever you substitute over here should be with the signs. Okay, so in general, if you have n charges and they are respectively at a distance r1, r2, r3, so on up till rn, okay, you can write the potential in this form, right? For one charge it is kq by r. For the system of charges you just add them. Okay, this k is taken common, so it is k q1 by r1, q1 by r1, k q2 by r2 plus k q3 by r3 and so on. Okay, so the k is taken common, so we have q1 r1, q2 r2, q3 r3, so on up till qn rn. Okay, for n charges, or you can write it in summation form, so basically qi by rn, right? It is of that form. So for continuous charges, this summation sign can be replaced by an integration. Okay, so here the potential will be 1 upon 4 pi epsilon naught, whatever the charge dq is, divided by r. Okay, so basically for continuous, you replace the summation with a integration sign. Okay, not of much importance for us. Okay, we'll move to dipole now. Okay, so for dipole, dipole is, if you can recall from the previous classes, it is a system. It is of two charges, two equal and opposite charges, right, separated by some distance, is a electric dipole. So minus q plus q separated by some distance. Okay, here O is the center of the dipole. Okay, and one important point is that r is always measured from the center of the dipole. I told you about this in the previous class, right? So r is always measured from the center of the dipole. Okay, not from plus q or neither from minus q. R is measured from the center of the dipole. Okay, so the field at the eggshell point, okay, on the axis of the, now this is the dipole, on the axis of the dipole, if you want to find field, the result will be kp by r square. Okay, actually it's kp by upon r square minus a square, but a is very small as compared to the distance r. Okay, usually in case of dipole a is very small, two equal and opposite charges separated by a short distance, right? So a is very small as compared to r, so you can directly write it as kp by r square. Okay, now in case of equatorial point, if you remember equatorial field, okay, here we also derived the relations for electric field in the last class, right? So there we got something over here, and this field at the equatorial point was also non-zero. But here in this case, the field at the potential at equatorial point is 0. Okay, so there is some at axial point, the potential is kp by r square. At equatorial point the potential is 0. Okay, whereas field is not 0 at equatorial point, and it has a value at both the regions. Okay, now if you want to remember these two relations, you can also remember it in a general way. The general way says that it is k p cos theta r square minus a square cos theta, or you can neglect that a square term. You can remember it as kp cos theta by r square. Okay, so if you substitute on the axis, what will be this angle? This angle will be 0, right? This is theta. On the axis, if you have the point, that angle will be 0. So cos 0 is 1, you get kp by r square. And on the equatorial point, what will be that angle? What is theta over here? It is 90 degree. On the equatorial point basically means on the perpendicular bisector of this dipole. Okay, so this will be passing from the center itself. Okay, point O, and this will make a angle 90 degree. Okay, So anywhere on the perpendicular bisector or the equatorial point, cos theta, theta is 90, cos 90 0. Equatorial point field is 0. Okay, or you can also find at any general angle, like suppose this angle is 60 degree. Okay, so these three relations, remember them, and these are few important results too. Okay, so with that being said, let's move to the next section. To our next section, which is equipotential surfaces. So what are these equipotential surfaces? By definition, it is a 3D surface on which potential is same throughout. Okay, a 3D surface on which potential is same at every point on that surface. Okay, so now let's discuss a brief special points about them. So potential difference between any 2 points on an equipotential surface is 0. Okay, this follows from the definition itself. So if you choose point A and B on this equipotential surface, okay, so if I tell you this is a equipotential surface for a point charge, okay, so here we choose point A and B for this surface, then you can see that the potential difference between them will be 0, because for a equipotential surface, potential is same at every point, right? So the potential at A is equal to potential at B, so VA minus VB should obviously be 0. Okay, so the potential difference between any 2 points on an equipotential surface is 0. Okay, let's come to point number 2. When Q naught moves from A to B on the same potential surface, no change in the potential energy, hence no work done. Okay, we'll come to the work done part now. In a while, I'll also tell you about the potential energy. So if we move from A to B, okay, if we move from A to B, what is the work done? We know that work from A to B will be Q naught. In terms of external force only, we'll write VB minus V, right, against. Okay, now from A to B, I told you there is no potential difference between any 2 points on the equipotential surface. So VB minus VA, these two have the same value, right? So potential difference is 0. Hence, this work done is 0. Okay, so this pretty much follows from here. Okay, since work done is 0 and electric force is conservative, you can express work as minus of delta U, okay, minus change in the potential energy. Work is 0, hence potential energy will also be 0. Okay, some books have habits of defining electric potential itself. They start this chapter from potential energy. Okay, they will define your work as your voltage or your potential as potential energy by Q. Okay, they start the chapter from here. Okay, they will define potential energy first and then they will come to electric potential. Okay, I started it from work. You can learn it that way also. Okay, so from there also you can see the potential energy will be 0. Okay, and hence no work will be done since this delta V is 0, right? Now let's come to the next point. Two equipotential surfaces can never intersect. Okay, this is just like two field lines can never intersect, because if two equipotential surfaces intersect, okay, so if this is surface A and this is surface B, these two are intersecting. Suppose we say that the potential for surface A is 40 and for surface B is 20. What is the potential at the point of their intersection, right? There is an ambiguity where it can be 40 or it can be 20. Okay, so we cannot allow such ambiguities. So it is necessary that no two potential surfaces can intersect each other. Okay, they never intersect each other. So let's come to the final point. Here we say as no work done into. So since if you move a charge Q naught from A to B on the same equipotential surface, we said that the work done is 0. It follows. So from here, from point 2, you can follow that the electric field is perpendicular to every point on the equipotential surface. Okay, we can relate to this. We can deduce this from the following relation. Since work is 0, we can say that F and D are in perpendicular directions, right? F dot D is 0, right? So F and D are perpendicular, okay, since they are not both 0, okay, or either one of them is not 0. So F and D are perpendicular, okay. So F also relates to E, okay, F is equal to QE. So F and E are in the same direction, parallel or anti-parallel, okay. Since F is perpendicular to D, F is perpendicular to the distance, okay, then E should also be perpendicular to the distance, okay, since they are both in the same direction, okay. So from here you can see that electric field is perpendicular to D, okay. So from here you see that electric field is perpendicular to D, and this D is nothing but distance along the your equipotential surface, right? So electric field is perpendicular to every point on the equipotential surface. Okay. Now this point can be used to find, you can construct the different equipotential surfaces. Like for point charge, the equipotential surfaces are found to be concentric circles. It is no surprise because for point charge it is kq by r, right? It relates to r. For every circle of radius r, the potential will be same, right? These two are constants. Okay, q is constant. Okay, you can fix some value, k is constant, we know that, and for every value of r you will have a fixed potential, right? So for a point charge, the equipotential surfaces are a system of concentric circles. Okay, so here we have this one equipotential surface. Suppose on this 20 volts, okay, and on this it will be 10 volts, right? Inversely proportional to radius, higher radius, smaller potential. Okay, so you can go on with the concentric circles. So for a point surface, and you can also link it with the concept that we learned previously, electric field lines. So electric field lines for a point charge is radially outwards, right? So you can see that at every point on the sphere it will be radially outward or making an angle of 90 degrees. Okay, electric field is perpendicular to every point on your equipotential surface. And similarly for a line charge, you can construct a cylinder. If you remember, for when we were finding electric field due to a line charge, we used a Gaussian surface as cylinder. Why? Because of this. Okay, so a cylinder is equipotential surface. Okay, so you can also make out here that the field lines that will be coming from the line charge will be also perpendicular to the surface. Okay, it's coming out in all directions, and cylinder is also like this, right? So it is perpendicular to every point on the equipotential surface. Finally, coming to this line charge, this is uniform electric field. Uniform electric field is shown by set of parallel lines, right? Parallel lines, equispaced lines. So this is uniform field, okay, like between the plates of the capacitor, you can say. Then 1 and 2, the parallel plates are forming the equipotential surfaces. Okay, so you can have a system of parallel lines, okay, that will form the equipotential surfaces. Here also you can see that electric field is perpendicular to every point on the surface. Okay, so those are different equipotential surfaces for different charge distributions. Please remember them, and let's move to the next section. So section number 4, here we will be discussing the relation between electric field and electric potential. Okay, it is a very important section, and a lot of questions are seen from this section. Okay, so here the relation, here we will be writing it directly, we will be obtaining the final result, and the derivation class will be deriving it. Okay, so here the relation that we are supposed to obtain is E is equal to minus dV by dr. Okay, so the electric field is the negative derivative of your potential. Actually, that is not the end of the story. Actually, this is a lie. Okay, even in your NCERT they have given is this like this, but this is only true for a single variable. Okay, so if your V has only X term or only Y term or only R term, okay, in that case this is true. Okay, or else your electric field is actually the negative gradient of your potential. Now gradient is a big term for you all, so I'll simplify it down for you. Okay, here it is important to remember that the negative sign shows that the field is in the direction of decreasing potential. Okay, initially we discussed, right, the potential goes from higher potential to lower potential, the field goes from higher potential to lower potential. Okay, so this negative sign over here, minus dV by dr, for electric field is showing that your field is in the direction of decreasing potential. If you remember the first question, it was from 40 to minus, I think 20 to minus 40, right? Potential is in the, field is in the direction of decreasing potential. Okay, now let us come to the actual truth. Okay, this is only true for a single variable. If your potential V is a function of single variable. Okay, if you have multiple variables like X, Y, Z, then in that case you are supposed to take partial derivative. Now by partial derivative I mean that when it is X, you only take in consideration X. Okay, when it is dV by dx, treat all other your variables as constants. Okay, so if you have suppose a function like xy and you want to differentiate it with respect to x, okay, then you will treat y as constant. I will come out and here x derivative of x is with respect to x is 1. Okay, so treat all other things as constant. Okay, all other variables as constant except x. In this case, treat all other variables as constant except y. Treat all other variables as constant except z. Okay, so here you'll obtain ex, ey, ez. Okay, filled in x direction, y direction, and z direction. You just have to relate them with their corresponding unit vectors I cap, j cap, k cap, and that will give you your electric field vector. Okay, now also from here you can follow it up that so if you see from here you can obtain potential in terms of electric field. So E dot dr and will give you dv, so integration of that will give you E dot dr, right? Integration of that will give you potential. Okay, and within the limits vb minus va. Okay, this is final minus initial, so final limit is b, initial limit is a. Okay, so vb minus va, final over here, initial over here. Okay, final minus initial, and this is also final, this is final, this is initial, right? Final limit, initial limit. Okay, so those are important point to remember, and dr can be written as dx I cap, dy j cap, and dz k cap. Okay, so let's come to problems now and let's see how much we have understood. Here we are supposed to find the electric field vector. So here we know that it is a function of multivariable. Now this is z, I just write it that way because it otherwise get mixed up with 2. Okay, so here we can see that it is a function of x, y, z, so we have to follow this logic. Okay, so ex will be found as minus dv by dx, right? So differentiate this with respect to x only. So in case of v I can write like this, right? So what does this give you? This will give you now 3y is a constant, z is also constant with respect to x, right? So only variable over here is 2x. Now 2x, differentiate that, will give you 2, right? And here there is minus sign. Now ey, similarly you do that, minus d by dy of 2x plus 3y minus z. Okay, here z and x are constant, 2x is also constant, and minus z is also constant with respect to y. Y only sees y. Okay, so here if you see derivative of 3y is 3 and this minus sign. Then ez and d by dz 2x plus 3y minus z. Here it will be the derivative is minus 1, right? Minus and this minus will make it plus. So your electric vector is ex I cap, so minus 2 I cap minus 3 j cap plus 1 k cap. Okay, let me check that. Minus 2 minus 3 plus 1. Okay, that is correct. Let's come to this one. Here we are supposed to find VAB. Okay, VAB basically means VA minus VB. Okay, so we are supposed to find VA minus VB. Electric field vector is given and RA and RB are also given. Okay, so if you see VA minus VB, okay, we'll use this formula. This is final limit, initial limit, right? So A is your final limit. So last position will be your RA, okay, and your initial position will be RB, position vector B. Okay, so yes, initial. So this is final, initial. Okay, and this is minus E dot dr. Okay, so E will directly substitute. E is 2 I cap plus 3 j cap plus 4 k cap, and dx, dr you know as dx I cap, dy j cap, dz k cap, right? So here you will obtain VA minus VB as, now RB you just place the components. Okay, since we are going to obtain this as, this is a scalar, right? So here RA and RB basically place the components. So that will give you the XYZ from this x to that x, right? So here if you see RB is 2, 1, minus 2. So we are moving from this coordinate to 1, minus 2 and 1, right? So we are moving the x coordinate from 2 to 1, y coordinate from 1 to minus 2, and similarly for z coordinate. Okay, and here we obtain, there is a minus sign over here, and here we obtain 2 dx. So I hope you know to take the dot product, I with I, j with j, so 3 dy and 4 dz, right? So this is what we obtain. Now we have to integrate. If we integrate, this will be 2x, 3y and 4z, right? Dx will become x, dy will y, and this will be z. Okay, so we obtain 2x plus 3y plus 4z, and this you have to vary from 2 1 minus 2 to 1 minus 2, sorry, 1 minus, yes, 1 minus 2 1. Okay, so that we'll do it over here. So that will be upper limit minus lower limit. Okay, substitute the upper limit. X is 1, y is minus 2, 3 2s are minus 6, and here 4 1s are 4 plus 4, so this is upper limit minus lower limit. So 2 2s are 4, okay, and this is 3 1s are plus 3 excuse me, and this is what is this, 4 2s are minus 8. Okay, so this will be what is this, this is cancelling out, right? This is cancelling out, and this will be, and there is a minus sign over here, right? Yes, so this is cancelling out, 2 4 6 6 cancels, and this minus sign, that minus sign neutralizes, 4 3 is 7, and we get minus 1. So minus 1 volts, right? It is potential difference. So this is in Newton per Coulomb, standard units. So minus 1 volt, yeah, that is your answer. So that was about the relationship between your electric field and your potential, electric potential. So over to the next section. Discuss an important concept, which is electrostatic potential energy. As I told you, the idea of electric potential itself can be brought up by electric potential energy. Okay, potential can be defined as U by Q naught. Okay, and you can start the whole discussion from there. Okay, but here we'll look it in a different light. We'll see it as a energy which arises due to the interaction between two charges. Okay, so you should have at least two charges for potential energy to exist. Okay, so the energy due to the interaction between two charges. Okay, that is going to be the potential energy. And here F is conservative. We have learnt it in the last chapter that electrostatic forces are conservative forces. Hence, the force can be expressed as a function of potential, specifically negative gradient of potential, but you don't worry about that. So force can be written as some function of potential. Okay, so in that case, work can be related to potential energy, as basically work is negative change in the potential energy. Okay, so work done from A to B will be negative change in the potential energy. Change in potential energy is U final minus initial, right? Change is basically final minus initial, and negative sign will flip it over, so it's initial minus final. So if you are asked about the work, okay, you just between two configurations. So if you have configuration 1, okay, of some charges, and then configuration 2, okay, if you change from 1 to 2, if you are asked for the work that is being done in this transition, you can just find the potential energy of this configuration and that configuration, subtract the two, and you will obtain the work. Okay, initial configuration, potential energy of initial configuration, potential energy of final configuration, subtract the two, initial minus final, specifically, that will give you the potential, the work that is being required to do that change. Okay, now let us discuss potential energy for different system of charges, like two charges. As I told you, it is due to interaction, so we must have at least two charges. So for two charges, the potential energy is given as k q1 q2 by r square, 1 upon 4 pi epsilon naught, this k q1 q2 by r square. It is important that you substitute q1 and q2 with sign, and basically if you want to visualize this, you can also imagine that potential energy is due to the work this charge q1 does on q2. Okay, so basically to set up these charges in q1 and q2 configuration, you have to bring the charge q2 from infinity to the distance r, right? So the work done in bringing the charge from infinity to that distance r will be stored as potential energy. So you can also weave it that way. Okay, and that this idea is going to help us a lot when we go to system of charges. Okay, so if you have system of charges, let us consider only 3. It will get more complex as we consider more and more. Okay, and the question will be doing 4. So let us understand it for 3 charges. Okay, so q1, q2 and q3. What is the potential energy of this configuration? Okay, so it will be k. First of all, k is, will be common, and you'll have somewhat of the form q1 q2 by r, q1 q2 q3 by r, and again q1 q3 by r. Okay, so something of that form. Okay, so how do you reach to this relation? So first of all, k will be common to all the terms, we know that. Now first of all, we will imagine that there is only q1. Okay, if you imagine it null, okay, there is nothing, you bring q1, that is no work done, right? q1 was brought without any existing electric field. There was no electric field, and so you could bring q1 anyways without doing any work. Okay, so no work was done in bringing q1. Now let us bring q2. Okay, so let us bring q2 from infinity to r12. Okay, so what will be the work done? It will be these two charges. Now these two charges will interact, right? So q1 q2, and what is the distance between them? R12. Okay, now when we are bringing q3, these two charges are present, so we can account for them individually, one by one. Okay, so when we bring q3, we can first consider q1. So we bring q3 at a distance of r32. So interaction between them, q1 q3, and the distance r13. Okay, this should be r13, sorry, right, this should be r13. Yes, and finally, since q3 was brought when q2 was also present, first we brought q1, no work done. q2, this term came. When we bring q3, this term will come due to q1, and due to q2, this term will come. q2 q3, the interaction between them, and divided by r23. Okay, it will become more clear as we go to this numeric. You can also write it in summation form, qi qj upon rij. Well, I is always less than j, I is less than j, I is less than j, I is less than j. Okay, so let's come to this one. Here we have square of side 1 centimeter, 1 meter. You are supposed to find the potential energy of this configuration. Okay, so we have q1 q2 q3 q4. Okay, now potential energy, as we can say, will go by the same concept. Here we'll write k, and first q1 is brought, no work done. Now q2 is brought in presence of q1. So we'll have q1 q2, the interaction between them, divided by the distance. Distance is always 1 meter, you can see. Okay, in some cases it might change, like for the diagonal. Okay, we'll account that. Now when we bring q3, okay, now q3 is brought in the presence of q1 and q2. Okay, we have q1 and q2 present, and then we are bringing q3, right? So the interaction between these two now, so q1 and q3 divided by the distance. Now what will be that distance? That is diagonal. Diagonal is root 2 times side, so that distance is root 2. Okay, and now finally coming to this. Okay, this the interaction between these two. Okay, since q2 was also present, that will also contribute. So we can write q2 times q3, the interaction, divided by the distance, which is 1. Now let us come to q4. When q4 is brought, all the three charges are present, 1, 2, and 3. So you have to account for all the interaction. So q4 is brought, so q1 q4 by the distance, which is 1. Then we have q4 and q2, q4 q2 divided by root 2. Yes, then we have q4 and q3, right? So q4 q3 divided by 1, right? Distance is 1. Now let us find this answer. That will be 9 into 10 to the power 9 k value. q1 q2 all are in microcoulombs, you can see. So whenever you multiply two of them, that will be 10 to the power minus 12. I can bring that common outside. Now I will just substitute sorry, q1s with the sign. So q1 q2, so q1 q2, q1 q3, sorry, q1 q3, yes. Okay, q1 q3, then we have, this is by root 2, then we have q2 and q3, q2 and q3, so 2 and 3, right, 2 and minus 3, plus q1 and q4, q1 and q4, 1 and 4, then we have q4 and q2, q4 and q2, 4 and 2, and root 2 is the distance between them. And finally we have q4 and q3, right? q4 and q3, 4 into minus 3. So whatever this answer is, you can calculate it. It will be 9 into 10 to the power minus 3 into what is this? This is 2 minus 3 by root 2, and here we have minus 6, and here we have 4, okay, and again we have 8 by root 3. I think this will cancel, 4 plus 2 is 6 and minus 6 cancels, and finally we have minus 12 sorry, 9 into 10 to the power minus 3, and this will be 8 minus 3, 5 by root 3 minus 12. Something answer you will get, some negative answer. I think it's minus 7.62 into 10 to the power minus 2 joules. Okay, you can confirm that. Okay, so that is about your electrostatic potential energy. Over to the next section. To section 6, here we'll be studying the potential energy of a dipole in uniform electric field. Okay, so you'll better understand this if you have seen dipole in a uniform electric field from chapter 1. Okay, so basically again focusing only on the final results, the derivations will be in the next video. Okay, so the change in the potential energy, if you change the dipole is basically plus q minus q separated by some distance. So if you change it from one theta to some other theta, the change in the potential energy will be given as Pe cos theta 1 minus theta 2. Okay, that is how you'll find the change in the potential energy when you change from configuration 1 to configuration 2, initial, final. Okay, now for most cases we consider the initial configuration as 90, because at that cos theta 1 will be 0, this will be 0, and you will be basically left with minus Pe cos theta 2. Okay, so basically if you are asked for the potential energy of a dipole in a particular configuration, the reference configuration you should take is that which makes this one 0. Okay, so basically final value, if you were given a theta and you are supposed to find your potential energy associated with dipole, so that will be minus P cos theta. Okay, or that will be minus P dot E. Okay, that is the definition of the dot product, right? And theta, it's obvious to say that it is the angle between E and P. What is P? P is your dipole moment, right? And the direction of P, if you have seen the previous class, it is from minus charge minus q to plus q. The direction of dipole moment is always from minus q to plus q. Okay, so dipole moment, we are studying this dipole moment in a uniform electric field. We studied it in the previous class that the net force acting on this dipole is 0, because if you see this is minus QE, that is plus QE, right? Minus QE plus QE, they will cancel out each other, right? So net force acting on this dipole is 0 in a uniform field, and the torque may not be 0. Okay, if it's placed like this, here you'll have a plus QE, suppose plus charge, and here you'll have minus QE, right? So here there will be rotation, it will cause rotation, and in this case torque is not 0. Okay, torque is not necessarily 0, force is always 0 for a dipole in uniform electric field. Okay, so this, due to this rotation, okay, it is storing some energy, right? So due to this rotation it will store some energy which will be in the form of potential energy. So this is the reason the dipole in uniform electric field stores potential energy. Okay, now if we see the two equilibrium conditions, so equilibrium basically means that the net force is translational and rotational equilibrium. So the net force is 0, so no translation motion happening, and net torque is 0, no rotational motion happening. So if you see in this case, here we have P and E in the same direction. Okay, P is from minus q to plus q, and electric field we have chosen it to be in this direction. So if you see, the angle between them is 0 degrees, right? They are parallel vectors, angle between them is 0, cos 0 is 1, right? So you will get minus P. So in this case the potential energy is minimum. Okay, and if you remember from class 11th, the configuration in which potential energy is minimum is your stable equilibrium. Okay, and the configuration in which the potential energy is maximum is your unstable equilibrium. Okay, there are many reasons as to why. You can refer your class 11th chapter, work energy, I guess, work power energy. Let's come to this. Here we'll have, here this is unstable equilibrium. So here we have minus q plus q. We have just rotated the dipole by 180 degrees. So the angle between E and your P vector, they are opposite to each other. So the angle between them is 180 degrees. So in that case, cos of 180 is minus 1. So that minus sign will nullify this, and you will get PE, which is the maximum your potential energy can be. Okay, and for that reason it is the unstable equilibrium. Okay, so that's about this simple concept. Over to the next section. To the properties of the conductor, we have the following properties, and it is important to note that these properties will follow under electrostatic only. Okay, in the next coming chapters we'll be seeing the charge in motion. A moving charge will produce electric current and also magnetic field. Okay, we'll be seeing that in the next few chapters. But for now, our first two chapters deal with electrostatic, and these properties hold under electrostatic. Okay, that is a key point to remember. Okay, so basically your conductors have free electrons, and that is the reason it conducts, right? So let us look at the following properties. So electric field inside a charged conductor is 0. Okay, this is a very important property which says that electric field will be always 0 inside a conductor. Okay, this follows from actually point 2. Point 2 says that excess charge resides only on the outer surface. Okay, so whatever charge is there, excess charge which is there on the conductor will only reside on the outer surface. Okay, so if you have excess charge on the conductor, it will reside only in the outside surface. Okay, it will not be there inside. Okay, so since there is no charge inside, you can use the Gauss law. Okay, this is a flux. You equate flux in two different ways. That is how we used to find the field due to different charge distributions, right? So here when you equate this, this is flux due to Gauss law. Okay, Q enclosed upon epsilon naught. You'll see that inside the cavity of your, sorry, not cavity, inside the bulk of your conductor, there is no charge, right? Charge only resides on the outer surface. So charge enclosed is 0, which means electric field should be 0. So electric field inside a conductor is 0 because excess charge resides only on the surface. Okay, so this point follows from point 2. Now let's come to point 3. Electric field on any point close to a charged conductor is sigma upon epsilon naught. Okay, you will see this in the case of your capacitor also. When we find the field for capacitor, it will come out to be sigma upon epsilon naught. If you remember, due to a plane sheet, the electric field was sigma upon 2 epsilon naught. So if you have two plates, it will be sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, which is half plus half 1, sigma upon epsilon naught. Okay, so electric field close to a charged conductor, just beside it will be sigma upon epsilon naught. And it is important to remember that sigma is inversely proportional to radius. This is a principle of something. We'll come to that something. It's at the very end of this chapter. Okay, sigma is inversely proportional to radius. Basically means that the surface charge density will be more if the radius is less. So if the radius, if you come over here in this figure, if you see the radius is less, the charges are very much accumulated, right? So point, if you have very something like a pokey thing, okay, a needle, pointed thing, okay, that will hold more charges than a spread out thing. Okay, so if the radius is more, like E1, if you see over here, radius is more, so the surface charge density will be less. Inverse relation, right? Radius is less, then surface, it can hold more charges. Surface charge density is more, and of course E2 will be greater than E1 outside, right? Inside the conductor the field is 0. Just outside E2 will be greater than E1. Now let's come to point number 4. Field lines are normal to the surface of the conductor. They should ring something. Since you have studied equipotential surfaces, you know that field lines are always perpendicular to equipotential surfaces. So you can also say that your conductor is in itself an equipotential surface. Okay, we'll prove it in point 6. So for now, electric fields are perpendicular to every point on the conductor. Okay, your conductor itself is a equipotential surface. We'll come to that. Here, point number 5, it says that Q suspended. So here we have a conductor. Okay, it's a conductor. Here we have the material inside. Okay, and we have created a cavity. Okay, so we just imagine a sphere, entire sphere, and we have created a cavity in between. Okay, and in that cavity, suppose we place a charge plus Q. Okay, then minus Q will be induced on the surface. Okay, this is also on the surface. Okay, on the surface of your inside sphere. Okay, so minus Q will be present inside, and further plus Q will be induced on the outer surface, just to keep the electrical neutrality, right? So minus Q was induced over here, right, in this cavity. Okay, then plus Q will be induced on the sphere, and this will reside only on the surface. Okay, And if you see that here, if we had not placed this plus q, okay, plus q, and if you see that cavity is a very safe place, right? Since if there is no charge over there, there will be no field, right? The electric field inside a conductor is zero. Okay, so this is a concept that we used in electrostatic shielding. Okay, you can place something over there and it will be safe from all the fields around it, right? So there will be no field inside that cavity since there is no charge. Okay, and charges only reside on the surface of the conductor. So like if you have a question regarding is it safe to be out or be in a car during lightning, it's common sense says that it should be safe in a car, and guess what, it is, because it's inside a cavity, right? That has its own limit. Anyways, here coming to point number 6, that will prove our point number 4. Potential of a charged conductor throughout its volume is same. Okay, so if you see your electric field inside a conductor is 0, first point, right? And electric field is minus dV by dr, right? So electric field is 0. This means this is 0, which means derivative of something is 0, then V is constant. Okay, so the potential is constant throughout the entire volume of the conductor. Okay, so it acts as a equipotential surface, and hence the electric field lines are normal to its surface. Point proven, right? So that's about your conductors. Let's move to the next section. Potentials due to various charge distributions. We have ring, disk, hollow conducting sphere, and a solid non-conducting sphere. Okay, again we have only the results. For derivations you'll have to come to our next class, okay, the next video. For ring, the field at a distance p, at a point p, at a distance x actually will be given as kq by under root r square plus x square. Similarly for a disk, ring is like a bangle, disk is like a plate. Okay, so for a disk, you have charge q distributed over its entire surface. Then the field at a point p at a distance x will be given as sigma 1 to epsilon naught bracket under root r square plus x square minus x. Okay, we'll derive these relations in our next class. So now comes the important point. Again, we discussed the electric field relations for hollow conducting sphere and a solid non-conducting sphere, right? We can relate to that. So those who have learned in the previous class can actually see the results matching over here, somewhat matching, since electric field is inversely proportional to r square, and here we'll only have the difference as potential is inversely proportional to 1 by r, kq by r, right, for a point charge. So and electric field is 1 by r square. So you can relate the previous results. So let us discuss for hollow conducting sphere. So if you have a hollow sphere or a conducting sphere, basically it's the same thing because the charges will only reside on the surface. So anyways it will act like a hollow sphere even if there is inside material. Okay, so this two will act in the same thing. So only if you have a non-conducting sphere, solid non-conducting sphere, in that case the charges will not move, right? Since it's a non-conducting material, the charges will not move, they will stay uniformly where they are present. Okay, so let's come to hollow conducting sphere. The field inside, now r less than r, capital R is the radius, r less than r meaning inside the radius, meaning inside the sphere, so that will be kq by r. Okay, kq by capital R, it's a constant value, right? R is constant, radius is constant, q on the sphere is constant, and k is a constant, and again on the surface you'll see the same value. Okay, so for a solid conducting or a hollow sphere, the basically the inside field and the field at the surface is the same, which is kq by r. Okay, outside the surface the field varies as 1 by r. Okay, it varies inversely proportional to 1 by r, where r is the distance, small r is the distance, capital R is the radius. Coming to solid non-conducting sphere, if you see the relations inside and the relations on the surface and outside the sphere will be the same. Outside it will be kq by r, okay, inversely proportional to r, and on the surface it will be kq by r, capital R, radius. Okay, constant value. However, inside the sphere, in this case the field is 0, right? Inside the sphere field is 0 in case of your hollow sphere because there are no charges. Field is 0, field is 0, field is 0, potential is constant. Okay, now coming to this, here the solid non-conducting sphere, you have charges everywhere. Okay, so even if you consider a small part inside the sphere, you will have the charges. Okay, so you'll have to use your integration to in order to find the answers of this, and the answer comes out to be kq by r, the same value at the surface, minus 1.5 raised to r square, capital R meaning radius, small r meaning your distance. Okay, distance from the center. R, small r is distance from the center. Okay, so if you plug in r is equal to 0 over here, you will get 1.5 times kq by r, right? You'll get 1.5 times kq, and proportional to r you'll get something like that. Okay, so this value is 1.5 times the value on the surface. Okay, whatever value you will get at r is equal to r, that value is multiplied by this 1.5. Okay, so you can remember that the peak value is 1.5 times the value on the surface. Surface value is same, kq by r. So then it falls to the same point, and then after that it's all the same. Okay, inversely proportional to r. So that's about different potentials due to different charge distributions. Let's move to the next section. To the second part of this chapter, electrostatic potential and capacitance. Okay, so capacitance is basically conductor. They are devices that store charge. Okay, so here, as I've told, capacitor is a device that can store electrical charge and hence electrical energy. Okay, we'll be seeing the relation for electrical energy that is stored in a capacitor, in a parallel plate capacitor specifically. So in practice, specifically, charge cannot be held at fixed points. Okay, you cannot just hold charge at a point in space. You have conductors to store them. Okay, conductors can store charge, basically that what it means. Okay, so capacitor and conductors can be used, these two words can be used in interchangeable ways. Okay, so don't get confused. So whenever I say a conductor, it means capacitor, and capacitor, it means conductor. Okay, so if you have an isolated conductor, so basically if you want to derive the relation for capacitance, if you see, the voltage will be directly proportional to the charge. Okay, whatever the voltage is, it will depend directly on the charge at the point. Okay, so here the constant is 1 by c when you convert V is equal to Q by C. Okay, V is equal to Q by C, or you can write C is equal to Q by V. Okay, so that is the relation that we obtain for capacitance. This C, the constant over here, is nothing but capacitance. Okay, capacitance has a SI unit of farad. Farad is a very big unit, so usually you'll see microfarad or even picofarad being used. Microfarad is 10 to the power minus 6 farads. Okay, or picofarad will be 10 to the power minus 12 farad. Okay, so that's about isolated conductor. If you have a spherical capacitor or a spherical conductor, its capacitance will be basically 4 pi epsilon naught r. Okay, you can see that capacitance is here in this case is directly proportional to the radius. So greater the radius, greater the capacity to store charge. Okay, coming to C, we have a parallel plate capacitor, the one that we are going to know most about. We are going to learn most about it. Okay, so here basically two parallel plates are kept, and one is charged plus Q, other one is charged minus Q. Okay, with this A over here. Okay, that was about the area A. Okay, so the two plates are charged, one is charged plus Q, other one is charged minus Q. Both the plates have the same dimensions A and B. So the plate area is same, so if they are rectangle, so they are of the same length and breadth are same of both the plates. Okay, and what else can we say? The distance is kept constant between them. Okay, so in that case, if you have plates of area A and the distance between the plates is D, you can define the capacitance as A epsilon naught by D. This is the relation for capacitance for a parallel plate capacitor. It is also important to note that the electric field at a point B between the plates of the capacitor will be sigma upon epsilon naught, just what we discussed, close to a conductor, right? So inside the between the two plates of the capacitor, the field is constant and it is given by sigma upon epsilon naught. As I told you, one plate is sigma upon 2 epsilon naught. So half plus half gives you 1. Okay, and at points A and C, the field is assumed to be 0 outside the plates of the capacitor. Okay, so that is about capacitance and capacitors, and let us move to the next section. section number 10, not a lot to do after this, so let's pull up our socks for this final stretch. So here we are going to discuss the effect of dielectric when it is placed between the plates of a capacitor, and we'll also see a relation for the force on a plate of the capacitor on one plate of capacitor due to the other one. Okay, so dielectric is basically in electromagnetic theory, if I tell you, it is basically an insulator. Okay, it's an insulator, but it allows electric field to be induced in it. Okay, so it's a weird element. Okay, so here we have first of all, what are the advantages of placing a dielectric? Basically, it will increase the capacitor's capacity, meaning now when you place dielectric between the plates of the capacitor, your capacitor will be suddenly able to hold more charge. Okay, so if you fill it completely, so in between the plates, if you fill the entire space between the plates of the capacitor with your dielectric, it will hold k times more. Its capacity will become k times C. Okay, if it's initially C naught, it will become k times C naught. So that will improve charge, because C is directly proportional to Q, right? So greater capacity means it will hold greater charge. Okay, so that is the advantage. If you partially fill, however, so if you fill the capacitor, if you fill T of the thickness, the total distance is D between the plates. So if you fill T amount with a dielectric, then the relation is like this. Okay, in your C naught will be A epsilon naught by D, right? And now it is modified to this when you place dielectric in certain T amount. Okay, so it will become epsilon naught A by D minus T plus T by K. K is the dielectric constant of the material, dielectric constant of the dielectric. It will be provided usually constant value, okay, a real number. And sorry, let's come to this. Now when you place dielectric, a field will be induced, as I told you, between the plates of the capacitor. Suppose the field is E, you can see that since there is plus Q over here, minus Q, something minus Q will be induced over here. Now this and this will not be same in magnitude, rather it will be less, since dielectric due to the own properties of dielectric material, and same plus Q will be induced on the other side of the dielectric. Okay, so if you see, this field is from plus to minus, right? Induced field is opposing the external field. The field between the plates of the capacitor is being resisted by your induced field. Okay, so due to this, you can find the net field, and from the net field you will obtain this result. You can write E net is E minus EI, and from there you can obtain this result that your surface charge density is the induced surface charge density will be whatever surface charge density over here is sigma, the surface charge density of on the capacitor, into 1 minus 1 by K. Okay, so similarly for charge also you can write, since these two are proportional. Okay, so that's about it. We'll be deriving it, as I told you, in the next video. So for a conductor, so in place of a dielectric, suppose you had a conductor. For a conductor, we know that this K dielectric constant, that does not make sense, but K will have an infinite value. Okay, infinite value meaning this will become 0, and whatever charge you give it, it will produce. Okay, so whatever charge is there on the plate, it will reflect in your conductor. Okay, because it has highly free charges, right? Whatever charge you give on the plate, it will reflect in the conductor. Then also E net will be 0, because since the same field will be produced, so Q plus and Q induced will be same as Q, right? That is what I said. So here also it will be Q and minus Q, and here also it's minus Q, right? These two are the plates and this is the capacitor. So E will be induced over here, E will be induced over here, these two will cancel out each other. Okay, so E net will be 0 when you place a conductor between the plates of a capacitor. Okay, also the force between the force on one plate of the capacitor due to the other one is given as Q square by 2 epsilon naught A. Okay, remember this result. Might be asked for numericals, and we'll derive it, as I told you, 100 times. Okay, and let's move to the next section now. Section 11, here we will discuss the combination of capacitors. They can be of two types. You can connect them in series or in parallel. In series, you can see that they will share the same charges. They will draw some charge from the battery, so plus Q, and hence minus q will be induced on the other plate, so that will induce plus q on this one, and that will induce minus q on the other one. So basically the charge on the two capacitors or n number of capacitors in series will remain the same. Okay, so when they are connected in series, the charge will remain the same, the potential will split, v will become v1 plus v2 plus v3 and so on. Okay, so using that relation, basically you can find the equivalent capacitance. Okay, so C equivalent, if you do that, will be given as 1 upon C1 plus 1 upon C2 up till 1 upon Cn, or in case of two capacitors, basically it is product upon sum, C1 C2 upon C1 plus C2. It's opposite to that of resistors, right? This result is obtained when the resistors are in parallel. Here in case of series, you obtain such a result. Okay, capacitor. And if you see, voltage and capacity are inversely proportional, right? C is equal to Q by V. Okay, so if you want to find the potential when you are given two capacitors, okay, so basically you will have V is equal to, you choose the other capacitor, since it's inversely proportional. Since if you want V1, the voltage on first one, you will choose the second capacitor upon C1 plus C2. Similarly, if you want the voltage on second one, you will take the total voltage multiplied by the other capacitor, inverse relation, other capacitor divided by the sum. Okay, let's come to parallel combination of this. Okay, here in this case they have the same potential, their charges will split. Okay, so you can see they are connected in parallel, so the potential here and the potential here will be the same. Some charge q is drawn from the battery and it will split among those two capacitors, right? Depending upon their capacity. Higher capacity means higher charge. Okay, so that is what it says, higher capacity is higher charge, q is directly proportional to c. Okay, in this case the equivalent is given as the sum of the two capacities C1 and C2, or in case you have n capacitors in parallel, it will be basically the sum of all the capacities of each one of them. Okay, and if you want to find the charge on each one of them, the charge on first one, so if you have suppose 2, then the charge on the first one will be total charge, which is drawn from the, name it as q, small q, total charge times same capacity, because direct relation, so total charge times same capacity upon sum, total charge times same capacity upon sum. Okay, now using all of this, we'll solve a problem. Here we are supposed to find the charge on all of these capacitors. Okay, so first of all, let us find equivalent capacitance, and let us find what is this charge which is being drawn from the battery. Okay, so C equivalent. So first of all, you see that this is a parallel combination, so that will give you 4 and 2 in parallel, that will give you 6, right? I can call it this, I can call it as C1 dash. So that will be, okay, basically C equivalent will be, this will be 6, right? 4 plus 2, 6 microfarad, right? And now this 6, okay, 6 is over here, you can replace this entire thing with a 6 microfarad capacitor. So this 6 and 3 are in series. Okay, so series 6 times 3 upon 6 plus 3. 6 and 3 in parallel in series will give you 2. Remember, you can remember it that way. Okay, it's a direct result. 6 3 is 18, this is 9, 9 2 is, right? So 2 microcoulomb. This is your net capacity. Okay, first we considered this in parallel and then those two in series. Okay, now if you want to find q will be CV, right? C is 2, C equivalent, right? C equivalent is 2 microfarad and voltage is 15. So you'll have the answer in micro, 30 microcoulomb. Okay, 30 microcoulomb is being brought out from the battery and it will be deposited on this one, since in series you have no choice but to take the entire charge, right? So here it will be plus 30 minus 30. So the charge on the first one will be 30 microcoulombs. Okay, so if you basically if they ask you for the charge on the capacitor, you only tell the charge on the positive plate. It is understood that the charge on the negative one will be just the negative value of this. Okay, now we have to find the charge on this one and this one. Okay, we can use actually this formula, or you can see that 30 coulombs will come over here also. Okay, right, this will have minus 30, right? So that should induce that should bring out induce 30 from there. Okay, from both of them. Okay, so the sum should be 30. Okay, so there should be some split between them. Okay, so if you see q2, you can actually divide this 30 into 6 parts. 4 plus 2, 6 parts, okay, and 30, that 4 parts should be given to the first one, 4 out of 6, and the rest of 2 out of 6 should be given to the next one, because direct relation, right? Greater the capacity, greater it will store. This will store 4 times 4 of the 6 parts, and this will store 2 of the 6, total 6, okay. Or you can use the same formula, you'll reach total charge C1 is 4 divided by C1 plus C2, 6, 30 or 2 same capacity divided by C1 plus C2, right? So this will give you 6 5s are 5 4s are 20, so this is 20 microcoulomb Q2, and Q3 is 10, right? So you got the charges on each of the capacitors. So that is how you do it. Let's move to the next section. Section 12 and 13 over here. So let's deal with them in one go because they are just short sections, okay. So the energy stored in the capacitor, as I told you, capacitor is a device which stores charge and hence electrical energy. So the relation for the energy stored is given as half q square by c, or you can substitute q as cv and obtain half cv square, or you can also obtain it in terms of q and v, but that will be half qv, okay. So you are supposed to remember all these three relations, at least one of them, and then you can derive others by substituting q as cv, and then here c as q by v, okay. Here coming to energy density is defined as this energy, electrical energy divided by volume, okay. When we derive it, it comes out to be half epsilon naught E square, okay. This is a standard result, you are supposed to remember it, it's very standard, and you will also obtain something of the same format for the magnetic field density, okay. It will be something of the same form, okay. Here if we have dielectric, the epsilon basically becomes k times epsilon naught, where k is the dielectric constant. Let's come to CR circuits, okay. So here we have a circuit with some voltage provided to it, and here is a switch. We have a capacitor and a resistor in the circuit. The capacitor is initially not charged, it is at 0 charge, and once we close this switch, what is going to happen? Current is going to flow, right, just for a short while, because at t is equal to 0, this capacitor will basically act as short circuit, okay. We will go into the depths of it in the next video, as I told you. So capacitor acts at t is equal to 0, capacitor basically acts as your short circuit, and maximum current will flow through the circuit, and in that attempt this plate will get positively charged and this plate will get negatively charged, okay. So there will be growth of charge on the capacitor, okay. This can be represented by this equation, the charge growth on the capacitor. It will be given as q is equal to q0 1 minus e to the power minus t by rc. Here rc is known as time constant, it might be also written as tau is equal to rc, okay. So, and finally at t is equal to infinity, the capacitor will be fully charged almost to 99.9% of q naught, okay, and that is what we call the steady state. And most of the problems that we discussed previously, or we will be discussing, are those in which the capacitor is in the steady state, okay. So there is a fixed charge on the capacitor, okay, so in steady state. So coming to the second part, which is discharging. Suppose now the capacitor is charged to some charge q naught, okay, and we want to discharge it to 0. So here we don't need the battery, we have removed the battery. So we'll just touch the switch, we'll put on the switch, and that will make current flow through the capacitor and it will slowly get discharged, right. So this is the decay of charge, okay, this is decay, that is charge growth, and this is charge decay. So this is the equation showing the decay of charge, q is equal to q naught e raised to minus t by rc, okay. So here the two natures of the graphs are shown. It starts from q naught and decays to 0, okay. At t is equal to infinity, it will finally become 0. Here also at t is equal to infinity, it will charge up to q naught, okay. So those are those two sections. Let's come to the final section of the day, which is our interesting Venn graph generator. Let's come to the final piece of the story. So the lights went off and you'll have to bear the aesthetic me now. Okay, so Van de Graaff generator, it is a device that is used to generate very high potential. Okay, you might ask what is the use of high potential. Those potentials are used to accelerate particles. Okay, using this Van de Graaff generator, you can produce a potential up to 10 to the power 6 volts per meter. Okay, the principle is very simple. It is based on corona discharge. Now I'm myself not very ashamed of telling you that I have very limited knowledge about corona discharge, so I would want you to read it. Okay, and sigma and one more key concept over here is that sigma will be very high at uh, places where the radius is very small, right? So the surface charge density will be very high if the radius is small. So basically, if you have something like a needle, pokey ends, there the surface charge density, those ends will hold a very large amount of charge. Okay, so the construction is simple. We have a metallic sphere. It is placed on an insulating stand. Okay, now we have two pulley system, like a conveyor belt, you can say. This belt is made up of insulating material. This brush we can call it, it is maintained at a very high potential, so it has a very um, it's a source of positive charges, you can say. Okay, so there is corona discharge over here. So basically the air leaks some amount of charge through the air. Okay, and it gets settled on the insulating belt. Now insulating belt will not allow the charges to move, so it gets stuck to the belt. Okay, and there is of course some amount of charge that just goes wasted. Okay, that gets neutralized. Okay, but most of it is carried on the belt to the, now this pulleys are driven by a motor, so of course this belt is rotating and this positive charge is driven to another brush which is connected to the metallic sphere. Now again here there will be corona discharge, leakage through air, and that charge will get settled on the metallic sphere. So more and more charge will settle on the metallic sphere, generating a higher and higher potential. It can go up to 10 to the power 6, right? That is where your air basically breaks down. Okay, so that is the principle of your Van de Graaff generator and how it is used to produce a very high potential. Okay, and I believe that to be the end of our story today. If you want to complete the missing pieces of the story, which are the derivations, do join me in the next class. Thank you very much for making it this far in the lecture and watching me in without the lights. Okay, so yeah, if you enjoyed this lecture, smash that like button, and if you are somebody who is going to give competitive exams, do consider subscribing our channel. It is a source it is a huge source, a gold mine for all the competitive exams. Okay, so with that being said, I say goodbye and keep enjoying physics.